Hi everybody. In this video I'm going to introduce chapter 2, and what that chapter focuses on are basic measurement issues and statistics, and we'll focus right now on the very first part of the chapter, so it's section 2.1. And what we're going to do is really distinguish between different types of data, specifically between qualitative and quantitative data. Let's go ahead and jump right in. So when we're describing key characteristics of data, we can describe data with a variety of different terms. And the reason why this is important is because some statistical procedures are appropriate for only certain types of data. Here's a good example. You've lived long enough that you've probably heard an average family has something like 2.5 kids or 2.8 kids. And we always kind of chuckle at that because we realize it doesn't make a lot of sense. There's not one family that you know of that has 2.8 kids. And that's because we realize that when you're counting number of kids, the only thing that really makes sense is a whole number. So someone might have no kids, or one kid, or two kids, or three kids, but you can't have 2.5 kids. And what we're dealing with here is a particular type of data that can't be broken down into fractional components, but we analyze the data by computing a mean, and means almost always end up having a fractional component. So we need to understand the type of data we're dealing with so we can understand what type of statistical analysis is most appropriate. Now I'm about to introduce a variety of terms. So for example, data can be qualitative, quantitative, and then we can break down quantitative data into discrete or continuous. And then I'm going to introduce even a few more terms to describe data. I don't want you to get confused and think that only one term would describe the data. Typically we have various distinctions that we can make. So for example, just like I can describe you in a variety of different ways, I can describe my data in a variety of different ways. So a student might be a sociology major, a student might be a female, a student might be 25 years old, a student might be a mother. I can describe that student in a variety of different ways. Same thing with my data. So here's the first big distinction that we'll make, the distinction between qualitative data and quantitative data. Qualitative data is non-numerical. It simply means that the data doesn't have any numerical meaning, any quantitative meaning. There are no quantities, no numbers. So a good example would be some type of question in which the response options are yes, no. So for example, do you have kids? Yes or no. There are no numbers involved there. So it's a very simplistic type of data. Now we can contrast that with quantitative data. Quantitative data is numerical and that it has numerical meaning. The numbers actually mean something. So now I might ask you, how many kids do you have? You can say 0. That would be like answering no. But now I actually have a number, 0. And that makes sense. It has numerical meaning. You might say 4. You might say 5. Bottom line is you're going to give me a quantity. So that's why we call it quantitative data. Now, quantitative data can further be broken down into discrete or continuous. Let's talk about that. Discrete data is indivisible. And because it's indivisible, meaning it makes no sense to divide up the numbers, only whole numbers make sense, there are limited values. It's limited to whole numbers. So a good example of that would be number of kids. So if I were to ask you how many kids you have, it really only makes sense to reply with a whole number, unless we completely overthink things. When we're counting people, only whole numbers make sense. So that would be an example of a discrete type of data. Now let's contrast that with continuous data. Continuous data is infinitely divisible, meaning we can continue to divide it up and divide it up and divide it up, and the number that we get always makes sense. So there are unlimited values. You want to think about it as a continuous number line, from the lowest number possible, like 0 kids, to the highest number possible. Now kids in this case wouldn't be an example because we don't have a continuous number line. 0 would be the lowest value, but then we would have to keep counting by whole numbers. 1, 2, 3. I need to think of an example where I've got between the lowest value and the highest value, every single point on the number line makes sense, and every single point in between makes sense. So let's change the example. Let's say I asked you how far you live from school. And someone might say I live 10 miles from school or 11 miles from school. And those numbers make sense. But you could also tell me that you live 10.9476 miles from school. And that number does make sense. So it's not a whole number, but it has appropriate quantitative meaning. So do you see what I'm saying? It's a continuous number line from 0 to the highest number possible, and every number in between makes sense when I ask you, how far do you travel to school? No matter what number you give me, that is a number that's appropriate for a continuous scale. All right, let's further talk about data in terms of measurement scales. So again, I can describe my data in a variety of different ways, and one way I can describe my data is in terms of the measurement scale that is being used. And you're going to want to think about these in order, because what happens when we move from a nominal scale to an ordinal scale to an interval scale to a ratio scale is we have all the properties of the scales before it, but then we get something new. And then we have all the properties of the scales before it, and we get something new with the interval scale. And then we have all the properties of the scale before it, and then we get something new with the ratio scale. So it makes sense to think about these in order. And one way that some people remember it is just by creating a word out of the first letter of each one of these words, N-O-I-R. And if you're familiar with French, it makes the word noir, which means black. You might have heard of film noir, kind of like a dark film. That's the way I remember it. But otherwise, nominal, ordinal, interval, ratio. Let's talk about them in order. Give you a couple examples. So first of all, the most simplistic type of scale that we can use to measure data would be a nominal scale. And nominal and ordinal scales tend to be associated with qualitative data, and interval and ratio level scales tend to be associated with quantitative data. Nominal scales are just names of unordered categories. So nominal means name. So you can see that this is a very simplistic type of scale because not only are we just dealing with names of categories, but I can't even order them in a meaningful way. So for example, let's say I was doing some marketing research to learn more about cell phones because I work for that industry, let's just assume. And I'm asking people, the next time you buy a cell phone, what brand of cell phone will you be looking for? So someone might tell me that they're going to buy an iPhone or BlackBerry or whatever it might be. And those are just names of categories. And because those categories don't have any type of quantitative value, there's no way I can order them from like largest to smallest. They're just names of categories. Okay, so let's move to the next type of scale that actually has more meaning, an ordinal scale. And you can probably see from the name ordinal that we're dealing with ordered categories now. So now we're just dealing with names of categories that can be ordered. So now let's say I'm doing some research and I'm asking people about the type of car they drive. And I want them to respond by placing their car in one of these categories. So I have something like compact car, mid-size car, full-size car, luxury car, SUV, something like that. You can see that there's an order that makes sense with those categories. So I have names of categories, compact car, mid-size car, full-size car. Those are names, but I can place those names in some meaningful order. Well, that's an ordinal level scale. Now, to kind of distinguish between these categories, you always want to ask yourself some critical question to see if you can move to the next category. So the critical question I would ask to distinguish these categories is simply, can I order those categories in a meaningful way? Now, the next question that I would ask is, even though I can order these categories in a meaningful way when I'm dealing with ordinal level data, I can't necessarily be assured that the difference between one category to the next category is the same amount of difference along the entire number line. So when I'm measuring size of cars, is the difference between a compact car and a mid-size car the same amount of difference, the same amount of change as there is from the mid-size car to the full-size car? I can't really be guaranteed that those are equal intervals, equal differences. Well, if I do have equal intervals or equal differences, I then have an interval level scale. So on a number line, all the intervals between the points are equal. And let me just give you a quick example of that. I'm going to go over these in a little bit more detail in just a second, and I'll quiz you on several things just so we can get a little bit of practice, because I know this takes a little bit of practice. So think about, for example, a Celsius scale. When we're measuring temperature outside, we have equal intervals. Because think about if it's 20 degrees Celsius or 21 degrees Celsius or 22 degrees Celsius. every full point on that number line has an equal interval. The difference between 20 and 21 degrees Celsius is 1 degree. The difference between 25 and 26 degrees Celsius is 1 degree. The difference between 37 and 38 degrees Celsius is 1 degree. So each point has an equal interval. So that critical question that we asked, are the intervals equal, would help us know if we have at least an interval level scale. Now you can see here an interval level scale though has no true 0 point. And in this case, the true 0 point means that 0 on the scale represents the absence of what it is we're measuring. Well, with something like measuring Celsius temperature, we're measuring heat essentially. And 0 degrees Celsius really isn't the beginning of the scale. It's not like that's where heat starts. Because of course we could have negative 10 degrees Celsius. So do you see how we don't have a true 0 point in that case? So you can see where the critical question is going to come into play to determine if we have a ratio level scale. If we have equal intervals and a true 0 point, then we have a ratio level scale. And the reason why this is important is because we often use ratio types of comparisons. So I might say that women are twice as likely to develop depression in their lives compared to men. Now don't quote me on that. I'm just giving you a simple example. But do you see how that's a ratio? I'm saying that women are twice as likely as men. Well, in order for me to do that, I need to have ratio level data, and that means I have to have a true 0 point. Well, let me give you an example of that. If we're talking about something like distance, I was asking you previously how far you travel to go to school. That scale is a ratio level scale because when I think of miles driven, let's just use miles as an example, we can have 1 mile, 2 miles, and the difference between 1 and 2 is a difference of 1 mile. On that number line, we can have 6 miles or 7 miles, and the difference between 6 and 7 is 1 mile. So every point on that number line we can see as equal intervals. The critical question that we need to ask ourselves now, is there a true 0 point? Does 0 on that scale mean the absence of what it is we're measuring? Well, what about 0 miles? 0 miles means you've traveled no distance. So it is a true 0 point. So with that type of data, with ratio level data like that, I could actually use ratio level comparisons. So let's say student number 1 travels 40 miles to school, and student number 2 travels 20 miles to school. Student number 1 does indeed travel twice as many miles to school as the other student. That's a ratio. Let me give you something visual that might help you see this a little bit better. Sometimes students do have a little bit of difficulty distinguishing between interval and ratio level scales, and want to make sure that you can see this a little bit better. Really, we have a great example when we deal with temperature in terms of Celsius or temperature in terms of Kelvin. As we mentioned before, Celsius would provide us with a scale that is only interval level. We have equal intervals along the entire number line, but 0 degrees Celsius does not measure the absence of heat. It's not the beginning, essentially, of the scale, because we know we can have negative degrees Celsius. So let's say we had 20 degrees Celsius. Let me try to make some marks here. Let's say we had 20 degrees Celsius, and let's say that was right about here. And then let's say I was comparing that with 40 degrees Celsius, and let's say that's right about here. I'm just arbitrarily picking some spots. Well, the beginning of this scale, when we really talk about the measurement of heat, the absence of all heat is actually at negative 273 degrees Celsius. So this is the beginning of the scale right here. So even though this right here is 20 and this is 40, we can see that 40 is not twice as much as 20, because we'd be going from here to here on that number line to measure 20 degrees Celsius, and from here to here on that number line to measure 40 degrees Celsius. Does this line look like it's twice as big as this line? It's clearly not. So with only interval level data, we cannot make ratio types of comparisons. But now consider a Kelvin scale. With the Kelvin scale, 0 Kelvin is really the absence of heat, which, if I understand correctly, is essentially defined as the absence of molecular motion. Well, regardless, 0 degrees Kelvin is right down here at the very bottom of the scale. So again, let's just use the same numbers to keep it simple. Let's say 20 Kelvin is right around here, and 40 Kelvin is right around here. Now when we look at those lines, we can see that 20 degrees Kelvin compared to 40 degrees Kelvin is in line with a ratio type of comparison, and that this line is twice as long as this. And I'm just using some simple lines to demonstrate that, but the point remains the same in that if we have a true 0 point, we can do ratio types of comparisons. All right, well, it's pretty important that we understand the type of data we have so that we can easily determine the appropriate type of analysis that we need to do. This pretty much just walks us through what I just said. All right, this chart right here just summarizes how everything fits together in that our data can be qualitative or quantitative. Remember, we have non-numerical data or numerical data. That non-numerical or qualitative data is typically measured on a nominal or ordinal level scale. And that makes sense, right? Because when we're talking about just names of categories, like the type of cell phone you plan to buy, there's nothing quantitative about it. It's non-quantitative, non-numerical, or qualitative. Quantitative data can be broken down into discrete or continuous. Discrete data is typically measured on one of these two scales, interval or ratio, as well as continuous data being measured typically on one of these two scales, interval or ratio. So this is how the data kind of fits together in terms of all the different ways we've talked about labeling our data with different attributes. Let's go through a couple examples, kind of quiz you. So classify each set of data as qualitative or quantitative. Brand names of cell phones in a consumer survey. Well, I guess we've been using this as an example. So the critical question I'm asking myself is, will someone's answer, when they provide a brand name, provide me with some type of number or quantity that makes sense in terms of numbers? And the answer would be no. So brand names are just categories, so they represent qualitative data. What about scores on a stat exam? So I want you to just kind of see my reasoning process here. I'm trying to determine, all right, what type of data would scores provide me with? They would provide me with numbers. So someone might get 95% of the answers correct or 90% of the answers correct. That's giving me a number that has some type of numerical meaning. So scores on a stat exam represent an actual count of number of correct answers, so they represent quantitative data. Now, I was expressing them as a percentage, but of course, we could just express those numbers as a count of how many items the person scored correctly. In either case, those numbers have numerical meaning. So now let's distinguish between discrete or continuous data. Indicate whether the data are discrete or continuous. Measurements of time it takes to drive to school. So the critical issue here in distinguishing between discrete and continuous is whether I have to limit my data to whole numbers or if the data I have makes sense along the entire number line. So from the smallest value to the highest value and every fractional component in between. So measurements of time that it takes to drive to school. So someone might take 10 minutes, 11 minutes, 12 minutes, and any number of minutes in between also makes sense. It might take you on average 10.54 minutes, and that number makes sense. So we must be talking about continuous data there. So time can take on any value, so measurements of time are continuous. The numbers used for calendar years, such as 2010, 2011, 2012, well, we never say that, it's September 2013 and 3/4. We just don't use years that way. When we're talking about calendar years, they are limited to whole numbers. So that's going to be discrete data. Calendar years are discrete because they cannot have fractional values. For example, this year will change from 2012 to 2013. The year will never be 2012 and a half. And of course, we're actually going from 2013 to 2014, and there will never be any fractional component. Let's go over another couple examples. Now let's talk about levels of measurement. Again, this is just another way to describe our data. Nominal, ordinal, interval, or ratio. Automobile classifications, such as compact, mid-size, or full-size. Well, here's the way you go through the reasoning process. Start at the most simple type of scale, nominal. So do we have at least names of categories? Well, we always have at least names of categories. So the critical question that we want to ask is, can we order these names of categories in some meaningful way? If we can, we at least have an ordinal level scale. And we can see here that we're going from compact to mid-size to full-size. This is the same example I gave earlier. Clearly, we can put them in some type of order. But then the critical question that we asked to see if we can move to an interval level scale is each interval along that line the same? Do we have equal intervals? So is the difference between a compact car and a mid-size car the same amount of change, the same difference as there is from a mid-size car to a full-size car? We can't be guaranteed of that. So ultimately, I only have ordinal level data in this example. All right, nominal, ordinal, interval, or ratio. Numbers on uniforms that identify players on a football team. So we're going to see various numbers on people's jerseys. So I want to try to determine what type of data I'm dealing with if I was collecting that data. So here we got like names of categories. So the names would be the numbers. Someone is number 99 or someone is number 12. Can I put those in some type of meaningful order? And remember, when we talk about meaningful order, we're talking about like from smallest to largest in some type of meaningful way. Well, in this case, although it seems like, well, we're dealing with numbers, those numbers are just naming the players. Those numbers are not describing something of any type of value. So number 99 on the field, does that mean 99 of something? No, it just means that's Steve. What about player number 12? Does that mean 12 of something? No, that means that's Jim. It's just another name for the player by using the number. So sometimes we really need to kind of think this out. That's not unlike zip codes, by the way. Remember, zip codes are just numbers, right? But they're numbers that represent geographic regions. So my zip code is 43821. Does that mean 43,821 of something? No, it's just a name that represents the Dresden area. So in this case, the numbers on uniforms are just simply naming essentially who the players are. They are simply nominal scale measurements. I can't even order them in some meaningful numerical way from smallest to largest. So ultimately, we're dealing with nominal levels of measurement. What about the weight of buns in ounces at the local bun factory? So in the Zanesville area, there's a bun factory that produces buns, I believe, for Wendy's. And of course, they do some quality control measures. So they might be checking the weight on the buns. So I'm trying to determine if I'm dealing with weight in ounces, what type of level of measurement am I using? So I've got like 1 ounce, 2 ounce, 3 ounce. So at least we've got names of categories, of course. Can I order those in a meaningful way? Well, yeah, 1 ounce, 2 ounce, 3 ounce. That makes sense in terms of a meaningful order. The next critical question, do I have equal intervals on that scale? So is the difference between 1 ounce and 2 ounces the same amount of difference as there is between 5 ounces and 6 ounces? And 23 ounces and 24 ounces? Yes, every single point on that number line has equal intervals. Now here's the critical question. When I'm measuring ounces for these buns, do I have a ratio scale? And a ratio scale needs to have an absolute or true 0 point. And that would mean 0 would represent the absence of what it is that we're measuring. So theoretically, would 0 ounces mean there's no weight, no ounces? And that's true, it does. So in this case, we have a ratio level scale. So if we had a bun that was 4 ounces, it really is twice as heavy as a bun that is 2 ounces. And again, the critical point is 0 ounces would represent no weight. And a true 0 point is necessary for a ratio type of comparison. All right, as we wind down, there is an interesting section of the book in the Time Out to Think section that talked about kind of an interesting little quandary that you'll probably be in. So let's just imagine this. On your group survey, you ask, which brand of cell phone will you purchase next? And we already know that brand names of cell phones would represent data measured on a nominal scale. Now let's say that this happens. When you enter your data, instead of actually putting in names like iPhone and BlackBerry and things like that, when you enter your data into Excel, you actually assign numbers. So 1 would be iPhone, 2 Samsung, 3 Nokia, and so forth. So my question to you is, did you now change that data? Did you change that brand name data from nominal to ordinal? Because it looks like I can order these in a meaningful way. So we'll talk about that in class. You can think that over. That's it. So that's all the key stuff from section 2.1. When we get together next time, we'll talk about the next section in Chapter 2. For now, that is all.